particle called neutrino. Have you heard the name neutrino? No. Yes? Ah, very good. So, story of the neutrino. Let me start with some quiz. So, here are some pictures. Okay? Some old men, some not so old, and not so old, they're old men. Some have died, expired. So now they have something in common. Do you know that? What is in common? I'll tell you. These are all winners of Nobel Prize. So they are all Nobel laureates. Okay? And 8 of them. They got Nobel Prize. But that's not all. There is something more common to them. They all got Nobel Prize to work on one particle. And that particle is neutrino. So look at that. There are 8 Nobel Prize already given to work on neutrinos. There is something more common among them. They are all experimentalists. There is no theorist. None of them is theorist. Okay? So they have all done experiment, something related to neutrinos, and got Nobel Prize. And I think in particle physics or no other areas of physics, you have 8 Nobel Prize for one particle. Okay? That's never happened. So that means something must be interesting about these particles that is getting again and again Nobel Prize to these people. You know? So this latest of them is 2015. These 2 persons got Nobel Prize. Okay. So now let me just try to tell that story, what is so special about neutrinos that is making so exciting in this area. So before that, let us put where neutrinos stand in terms of basic constituents of matter, that is basic building blocks. Everything is made out of, everything is made out of what? What you are, ultimately, if we start breaking things, what you will find inside? Atoms, good. If I break the atoms, what is it? Electrons, protons, neutrons. Good. If I break some of them, what I will find? Quarks. Fine. So where do you find the quarks? Inside what? Inside protons and inside neutron. Will you find quarks inside electron? No. Because electron itself is fundamental. So there is nothing inside it. And quarks are fundamental. So that's what I am putting here, all the fundamental particles. You see here, what we have are these fundamental particles called quarks and leptons. So let's look into quarks. There are 6 of them. There are 6 of the lepton. So this is total 12. There are 4 particles, I'll talk about that. This makes it 16. And there is Higgs, 17. These are the basic particles we have to discuss now. 17 particles are there. Everything you can, all things you can explain by these 17 particles. Now, out of that, these 2 particles, here, the quarks up and down and electron, they are a little special. Why they are little special? Because a proton, you said the atom is inside atoms, you have proton and neutron. A proton is made out of 2 up quark and 1 down quark. Okay? A neutron is made out of 2 down quark, 1 up quark. So, and proton and neutron makes nucleus, be it hydrogen nucleus, each side have 1 proton, or a uranium nucleus, you have 92 of them. So now, so basically you need only this, and the electron goes around the nucleus to make all the atoms. So if you have these 2 quarks and this electron, that explain everything that we see in nature, that we see. Remember my word, that we see. So visible world is made out of these particles. But for some strange reason, the nature has more than what we need. So for some strange reason, along with up and down, there is 2 more quark doublets, quark pairs, I will call you. Okay? This is called charm and strange, and this is called top and bottom. Somebody call it truth and beauty, but more we call top and bottom. These are the quarks. These additional 4 quarks Really you don't need, because our atoms and molecules, you, me, they are not made out of these quarks. They are all made out of these quarks. But for strange reason, nature decided to have duplicate of them and twice. Okay? These quarks are just like them, but only they are heavier. Their mass is heavier. That's all. Similarly, in the electron, we know electron, but electron also its heavy cousin, heavier cousins. For example, a muon is just like an electron, okay? But only it is heavier, 200 times heavier than the electron. And there is this tau meson, this is called tau leptons, which is something like some 3,500 times heavier than this electron, okay? So these things are there, but see, these things is coming in pair, up and down. Similarly, these fellows also come in pair. Electron has its pair, but electron's pair is a neutrino. Muon's pair is also a neutrino. Tau meson's pair is also a neutrino. But these three neutrinos are little different in their properties. Okay? So that's what is all about. So this is this 12 particle. Then there is this particle called bosons, in the name of Satyendranath Bose, Indian scientist, who actually discovered or proposed how this particle will behave actually. Okay? That's why they call bosons. For example, a photon is these are the carrier of forces. For example, you say inside the proton you have two up quark, one down quark. Okay? How do they stay together so close to each other? Because some force is acting among them. And that force is called strong force. And this force is being carried by one particle called gluon. Okay? Actually 8 of them, but gluon. Similarly, this photon is the carrier of electromagnetic field. The two electrons, when they come to each other, what do? If you bring two electrons close to each other, what will they do? They will repel each other. Why do they repel? Because there is a force acting. That force is called electromagnetic force. If you bring one proton and an electron, then they will attract each other. That is also because of the electromagnetic force. Okay? These forces, the force, see, I am here, a proton is here, an electron is here, but still they will feel the force. They are at a distance. So why they are feeling the force? Because they are exchanging that particle between them, that photon. Similarly, the quarks inside a proton, they are exchanging this particle called gluon. Okay? That's why they are feeling that strong force. And these are the particles for another force called weak force. Okay? This weak force, you don't realize is very weak, but it is responsible for all the radioactive decays. Okay? All the particles, uranium, that's called radioactive, right? We call uranium is radioactive. And that's basically because inside that, particles are decaying. Okay. Similarly, now, so this is about the particle. But my story, in fact, these particles, up, down, electron, they play a major role in our universe because the whole universe is made out of them. These neutrinos is not anywhere there. They are not inside the atom. They are not inside the nucleus. But my story today will be about those particles. What do they do? Why they are important? Why so many Nobel Prizes coming to that particle? And why there is so much excitement around the world for further research on those particles. That's what I am going to talk about. Okay, before that, see, you have no alpha ray, beta ray, gamma ray? Okay, you know alpha ray, beta ray, gamma ray. So this alpha, so you have a radioactive source. If you keep it there, it may emit alpha ray, it may emit gamma ray, it may emit beta ray. But there is some difference. All the alpha rays that comes out from a radioactive source has the same energy, exactly same energy. Okay? All the gamma rays that come out of a radioactive source have the same energy. Okay? That's it. But the beta rays, they comes out with different energies. They can have very little energy, they can have a very large energy. Okay? So they have a wide spectrum of energy. I have explained that in this picture because this is actually, you have put in a magnetic field. the particles are put in a magnetic field. So they are curving. Your charged particle, you see the curvature of this alpha particle are exactly same. The gamma particle, of course, they are neutral, so they will not be affected by magnetic field, so there is no curvature. But the beta particle, some is more curved, some is less curved. That is because their energies are different. You can explain that by this plot. If you plot the number of beta rays as a function of what energy they carry. So this is the energy and this is the number. You will see that they can carry as small energy but also a large energy. Okay? So the spectrum is like that. So this is basically a carbon is decaying to a nitrogen with the emission of a electron and an antineutrino. This is a source. Okay. Now, so physicists were all puzzled last century at the beginning that why this is happening. Okay? And then, so for example, if one nucleus is decaying to another nucleus through the emission of one beta particle, okay, so then how much the energy of the beta particle should be? What is the energy difference between these two? And whatever is the energy difference between these two, this is a constant number. So that energy should go always to the beta. So beta should have unique energy. So the puzzle was that why the beta has sometimes more energy, sometimes less energy. And that puzzle physicists, there are certain conservation law in science. You know that? Conservation of mass, conservation of energy, conservation of momentum, and so on. This energy conservation is a very, very heart of, one of the, strong pillar of modern science. So conservation law, energy conservation law cannot be violated. But if you look at this one, see, their energy difference should go to the beta rays. So where is the energy going? So people thought that maybe energy conservation law is violated. Even Niels Bohr, famous physicist, he says that maybe energy is not conserved. However, there is this gentleman called Wolfgang Pauli. He was not ready to accept that. So he was thinking how it is possible. How can this be explained? What is then proposed finally? That, well, so maybe when this nucleus is going to this nucleus, not one particle beta is emitting, maybe along with that some other particle is emitting. And then he called this, actually he didn't call it neutrino, he called this neutron, because that time the real neutron has not yet been discovered. This is in 1930 that he said. And then this energy difference between these two can be shared between these two particles. So sometimes this fellow can take a bigger share, and sometimes this fellow can take a bigger share. So you can explain why that energy is spread out. Okay? So that was the idea he came, and of course this was the idea, but it took very long time to discover that particle that he proposed in 1930. It is in 1956 when Reines and Cohen, two physicists from United States, they joined together to do an experiment to detect that particles. But to detect that particles, you have to find a very strong source of neutrinos. Why a strong source of neutrinos? Because by that time, another physicist named Enrico Fermi, he has shown that if that neutrino exists, it doesn't interact much. It almost non-interacting. So if it doesn't interact, so then how do you detect it? You have a large, when I say doesn't interact, it doesn't mean zero. It interacts sometimes. So if you have, so how do you get some number of events? You have to have a very strong source of those particles, neutrino source, strong. Then some of them will interact. Okay? If you have 1,000,000, in one of them interact, then at least you will get one event. But if you have 100, you will not even get one event. So you have to have a strong source of neutrinos. So how do you find a strong source of neutrinos? Till that time was cosmic rays, but that was not a strong source of neutrinos. But something happened during World War II and just afterward that changed the whole scenario. And that is called nuclear reactor. Nuclear reactor is the controlled way of having fission, and in the process, when fission occurs, the heavy nucleus get converted into two lighter nucleus and some neutron emits. Okay? And that neutrons again further destroy the other nucleus and so on. So that is a chain reaction. So neutrons are continuously getting emitted. And this number of those neutrons will decay into an antineutrino. All the neutrons will decay into antineutrino and proton. Okay? And a electron. Okay? So now, so that has become a source of antineutrino. And in a nuclear reactor, since many such neutrinos are produced, you can go to a nuclear reactor and try to detect some of them. That's what these two physicists did. They actually did an experiment. So let me just tell you. So this is the process. This antineutrino, electron neutrino, is being produced inside this reactor. They comes out and they hit a proton and they convert it into a neutron and a positron. So the positron you can detect immediately because the positron will immediately catch hold of a new electron, and though both positron, particle and antiparticle, they do annihilate, right? So, and then they will produce gamma rays, and this neutron also will get captured little later and will produce gamma rays. So you can see that signature, beautiful signature, and that's what they did in 1956. Okay? So it took a long time. Now this is, I have told you already, one source of neutrinos. But is that the only source of neutrinos? Somebody says cosmic rays. So let us look at that. Where are these neutrinos coming from and why they are important? You know how the universe was created? When the universe, at the beginning, it was all photons and lights and what you call the elementary particles. Those elementary particles like quarks, electrons, neutrinos, they are all there hitting each other. Okay? A neutrino and antineutrino is colliding, producing two photons. Electron and positron colliding, producing photon. Photons are colliding, producing those particles. So there was a thermal equilibrium at that time, and there was a large number of those neutrinos. But along with that, the universe was expanding. Okay? When that expanding means it is also cooling down. Okay? It's like if you have a hot ball of something hot and then it expands, it also gets cooled down. So when it is cooling down, then that interaction was not anymore happening. The thermal equilibrium is lost. Then the neutrinos that time came out freely, and those neutrinos are there everywhere. Those are called Big Bang neutrinos. Neutrinos from Big Bang. You know, those neutrinos, just like those 3-degree black body radiation you have heard of, you know, this, it is like those neutrinos created at the beginning of the universe. They are all around us. How many of them? How many of those neutrinos are there right now? You take your fist inside, every cubic centimeter, you have 300 such neutrinos created during the Big Bang and going at the speed of light all direction. So they are all there. 330 neutrinos. So imagine how many neutrinos are there in this room. 330 neutrinos per centimeter cube. So these are the neutrinos are there. Only problem with them is that they, because they have created at the early Big Bang and they are cooling down from that time onward, they have cooled down so much that their energy is very feeble. Their energy is something like 10 to the power minus 4 electron volt. Okay? Electron volt is roughly the energy you need to excite the atomic electrons, right, from one level to another. Hydrogen ionization potential is 13.4. So electron volt. So like that. So this is extremely small energy, and because of that, we are not been able to detect them so far. But if somebody in the future detect that neutrinos, no question there is a Nobel Prize waiting. So people are thinking how to detect the neutrinos, but we have not a mechanized way how to detect them. Then neutrinos are coming from the sun all the time. What is happening in the sun? Why do you get energy from the sun? Nuclear reaction. What is that? Fission or fusion? Fusion. What is happening? What is fusing to what? Good. Very good. So hydrogen is getting into helium. Here. So 4 proton is converting into 1 helium. So that means 2 of the proton must be converting into 2 neutron, because inside a helium you have 2 proton and 2 neutron. So when a proton gets converted into a neutron, it will emit, that is a weak interaction, it will emit 2 electron and 2 neutrinos also. Okay? Proton going to neutron plus electron plus a neutrino. That's the process. And some energy. Okay? So some energy. So since every 4 proton you get 2 neutrinos out of the sun. And if you calculate the total number of neutrinos that is coming from the sun and hitting Earth, every square centimeter of the Earth, this will be something like 10, actually not 10, 70 billion. Okay? 7 into 10 to the power 10. 7 into 10 to the power 10. So many neutrinos are from the sun every second hitting every square centimeter of the Earth. So they are coming. They are hitting you also. Okay? They are going through your body at the speed of light. Now, then there are neutrinos. So every star, sun is a star. So every star, when they are burning, they are producing neutrinos, this number. Then what happens when their burning is over, the fuel is over? Then the star can explode into a supernova. You know, when they blow up the supernova, even that time they produce a large number of neutrinos. For a short time, maybe 10 seconds, the boom, the star becomes a supernova, and then you get a burst of neutrinos coming from that star. And that will be really a great phenomena to observe, and we have only observed once. In 1987, one of the supernova in our nearby galaxy exploded, and those neutrinos came and hit two detectors, one in Japan, one in the United States, actually a third one also in Russia, but small number. They hit that, and then, so this will also give you neutrinos. Then somebody says cosmic rays. So yes, the cosmic rays are not really neutrinos that way. Most of the cosmic rays are charged particles like proton, helium, hydrogen, and all think of that one, oxygen, nitrogen, up to iron, nucleus. So they come with very high energy and hit our atmosphere. When they hit the atmosphere, they produce many other particles. Most of them are called pi mesons. These pi mesons are unstable particles. They are not stable. So they quickly decay, quickly convert them into this muons and neutrino, muon neutrino. Okay? So then they become source of neutrinos. Because they are produced in our Earth atmosphere, we call them atmospheric neutrinos. These neutrinos, you should be proud of, was first detected about 100 miles from this place where you are sitting right now, at the Kolar Goldfield Underground Laboratory in 1965. The first time in the world it was detected at Kolar Goldfield. Okay, so then there are also other high energy neutrinos and radioactivity in the core of the Earth. Then we can create neutrinos. Human beings also can create neutrinos. Not in a small anything. If you build a particle accelerator, you can energetic particle, they can hit some object and then produce pi mesons, and they will decay and produce neutrinos. So they are also produced. This is called man-made neutrinos. Of course, there is another source of man-made neutrinos called reactor neutrinos, right? That I have already talked about at the beginning. So these are various different kinds of neutrinos that we have, coming source of neutrinos of different energy. Now let's look at some number. Okay? Sorry, what happened? Okay. So close encounter with neutrinos. Every second, your body, as well as my body, is receiving about 1 trillion neutrinos from the sun, about 50 billion neutrinos from the natural radioactivity of the Earth, about 10 to 100 billion neutrinos from nuclear plants all over the world. It doesn't matter whether the nuclear reactor is there, because neutrinos penetrate everything and comes to you. Okay? It comes from the other side of the Earth and hit you. So imagine so many neutrinos are going through your body all the time. Scared? Must be. So many neutrinos going. Not only that, do you know each of you are producing neutrinos? No? Look at how many you are producing. Your body, something has 20 milligram of potassium 40. Everybody, any human, take some less, more depending upon your weight. Roughly, a normal human body has 20 milligram of potassium 40, and this is radioactive. You have radioactive material inside you. So they are all the time emitting beta decay. Okay? So along with that, neutrinos. And how many neutrinos each of you are producing per day? Each of you are producing 340 million neutrinos per day. Each of you. What are the neutrinos doing? Coming out of our body and just at the speed of light, just started moving, going to the other end of the universe. So, what does it mean? From this time of your birth, till you die, this 340 million neutrinos per day coming out of your body and becoming part of the universe. So that means part of your body is always becoming part of the universe. So when I tell that story, I also, when I give it to our political leaders, I always tell them, see, in our country, there is a custom that if some great man died, we take his ashes and then spread all over the country. So I tell them, don't have to do that, because all of our body parts is becoming parts of the universe all the time. So what is this big deal of spreading your ashes? Okay, so that's about it. But now with all these neutrinos, you must be scared that, okay, so many neutrinos, I don't know what is going on, because people always talk about radioactivity. They are bad. They are bad for human beings. So what is this? I mean, these neutrinos are going through your body. So what are they doing to you? Nothing. So you be rest assured. Good news is that, so if you want to stop a neutrinos, typically you have to put so many people one after another and shoot a neutrino. That neutrino may be able, then you will be able to stop. This is 10 to the power 19. There are 19 zeros. So that is impossible. So almost impossible to stop neutrinos. Okay? So that's the good news. But that's the good news for you, that neutrinos are not doing anything. But imagine those guys who want to catch those neutrinos. They want to detect those neutrinos. Those experimentalists, poor guys who have to spend time to detect them and study their properties. What about them? Unless they detect them, they stop them, they can't study them. So it is a really big problem for them. So a good news for you is a bad news for the neutrino hunters. Okay. So now let me just go how to detect neutrinos. See, even I said that it is almost impossible to detect neutrinos. I said almost impossible, not impossible, because they have very, very feeble interaction. So if you have a large number, you can detect some of them. Okay. Now let's start with the neutrinos. From the sun, what is happening? In the sun, 4 proton is getting converted to a helium and 2 positron and a neutrino and 25 wave energy. Okay? So that's what I said. So now, how do you detect these neutrinos? There is a famous physicist, Italian physicist called Bruno Pontecarvo. He suggested that for the first time. He says that if you have chlorine-37, you accumulate them, he calculated the spectral energy levels and all those things, it can absorb this electron neutrino coming from the sun and convert itself into an argon. So the chlorine will convert into an argon, okay, by absorbing this electron neutrino. Simply what is happening inside the chlorine, okay, so simply that, it coming out with 1 electron. That means 1 neutron inside the chlorine is getting converted into 1 argon, okay? Because proton, sorry, opposite, neutron, so proton is getting neutron is getting converted into proton, not, okay? Neutron is getting converted here in the proton, okay? So now, this is easy to say how to detect that. So there is a guy who is one of those Nobel laureates. So he actually decided that he will put this C2Cl4. This has lots of chlorine in that. You can't get just chlorine, so you have to get some composite of chlorine. So carbon tetrachloride, he put it that in a experiment underground in the Homestake mine in US. 100,000 gallon of that, okay? And then is looking that some of this chlorine is getting converted to argon or not, okay? This has actually, this chlorine means it has mostly chlorine 35, because that is the major isotope. But only small fraction of those chlorine is chlorine 37, okay? And only chlorine 37 will absorb this and convert it into argon. So what he has to do? He has to put this thing underground in a big tank, and somewhere this chlorine is getting converted into argon, and every month he will churn that liquid and pick up some only few atoms of argon that is there. So that itself, it is a big thing to do. So yesterday my colleague was telling that you can example that one, that you have to go to Sahara Desert, okay? Sahara Desert, and you take out 1 grain of sand from there and paint it in a different color, okay? Paint it, let's say red, and put it back Now your job is to search that 1 grain of salt. Because in this tank there are billions of this chlorine 37. And in that only 10 of them may be argon getting converted. So you have to pick up those 10. So he did that experiment and he succeeded in doing that one. And that's why he has managed to do that. That is process, you can convert how, it's a chemistry. It's a process of chemistry. So this man, though he got a physics Nobel Prize, he was a chemist. So he could do that experiment. And he got this from the sun, neutrinos coming from the sun. So that is the first time that what was proposed about the nuclear source of solar energy has been established, because this is the correct theory. I am not going to talk about that, but then there are one problem he found. See, I have told you, what is the neutrino that is created in the sun? What kind of neutrinos? Did you notice? I said it, no? What kind of neutrinos is created when proton is getting converted into neutron? There are 3 kinds of neutrinos. I told you, electron, muon, tau neutrino. Electron neutrino, remember that. So this guy was trying to detect electron neutrinos. He found them, but only problem is that he was expecting something like a number 8, but he got a number like 3. They're all less, na? This is expected. So that means he got neutrinos from the sun, but didn't get enough. So that was his problem. So that was a puzzle, that neutrinos are emitting from sun, but not enough to explain the luminosity of the sun. So what is happening? So there are 2 possibilities. I mean, soon other experiment also came, and all the experiment, they are expecting this, and they all found less. Some were up, some were 1/3, like that. So all these experiments, this color is basically experimental data, and this yellow one is what they expect. So always, all the experiments they did for solar neutrinos, they all got less number of neutrinos. So where is the neutrinos going? They are created in the sun, but not reaching to the earth. That's what is happening. Not all of them reaching to the earth. Only 1/3 is reaching, or half is reaching. So that was a puzzle. How to solve that puzzle? The puzzle came, solved the puzzle. Let me just tell the story short. This was solved in this way. Okay. So I will not give it the story. That the story is that the electron, there are 3 neutrinos, no? So the science is that the sun, when it started as electron neutrino. But by the time it reached Earth, it has got converted into a muon neutrino or tau neutrino. That's what they said. So this is called, that means neutrino, electron neutrino is becoming tau neutrino, is becoming again electron neutrino. So electron is oscillating from one stage to another. And you are looking only for electron neutrino, you are not detecting them. So then one experiment was carried out in Canada. They has the ability to detect all 3 neutrinos. Whether it is a muon neutrino, tau neutrino, they will detect it. And when they did that experiment, they proved, this experiment I am not telling, that, these 2 numbers. See, they saw the exactly same number. So that means that explanation was correct. See, this how ideas come. So first there was an experiment. They found less number of neutrinos, and that to explain, the people gave the theory that neutrino oscillates from one type to another. So then they did another experiment and proved that that is happening. So this is how in science, in research, you go together. I mean, you get some result, unexpected result, then you scratch your head, try to explain that with new theory, and try to prove that later by doing more experiment. Okay? That is how it is done. Okay. So now, so this is the time, I wanted to show you that in atmospheric neutrinos, I told you, was first detected at Kolar gold field, and this is the experiment that detects that one. This was kept actually at 2.3 kilometer underground. Okay? At 2.3 kilometer underground at Kolar gold field, they did that experiment. And how is the neutrinos? Neutrinos you cannot detect themselves, because neutrinos are neutral particles. You cannot detect them. But what happened? The neutrinos come, and there is rock around, no? In the rock, they interact. An electron neutrino will produce an electron if it interact at all. I mean, first of all, I said to you that it doesn't interact. But if at all it interacts, electron neutrino will produce an electron. A muon neutrino will produce a muon. A tau neutrino will produce a tau, never other way around. Okay? Electron neutrino will not produce a muon, or a muon neutrino will not produce an electron. Okay? So then that is how you know that there are three kinds of neutrinos, because you look at that. So here what they did, this experiment you are seeing, that whenever a muon is going through, they will detect that. Okay? They will detect that muon. And that's what they detected the neutron. But how do you know that muons are also can be coming from cosmic rays and straight coming there, not from neutrinos. But those muons will get stopped. Cosmic ray muons will get stopped in the 2.3 kilometer rock that below it this detector is located. So no cosmic ray muon will reach here. But neutrinos, I told you, they are penetrating everywhere. So they will come there. So, and they will interact. Some of them will interact, and then they will produce a muon trap. And that is how the KGF group detected that experiment, detected that neutrinos. So this is so this is like, the neutrinos, if you want to detect, you have to first filter out all the other particles. Then only you will be able to detect. Because otherwise it's like that. If you want to detect starlight, what you have to filter out? Starlight, you want to see starlight. Huh? Exactly. Tell me. Yes. You have to, because sunlight is much more number than feeble starlight. So you have to stop the sun from shining. That's why you see in the night only stars. So similarly here also, if you want to see the neutrinos, you stop all other cosmic ray particles. How do you do that? Go underground. Because all other cosmic ray particles will be absorbed in the rock above, and only neutrinos can reach there. Then you detect happily. So sometimes, even to look at the sun, you have to go to underground, inside a tunnel. Okay? And it's like that. If I stand here, I will not see anything. It's all these things. But if the lights penetrate this body of this wood, I will be able to see you all, transparent, right? If I put a block of glass here, I will see you. But if I put a block of wood here, I will not see you. It's like that. Okay. So this experiment, and this is one of these events, see, for later on we did that. This is muon. See, this is what you see. A neutrino has come like this from the bottom of the earth, and then interacted and produced this muon. Okay, this is a muon, this is a pi meson. And then you see that. Suddenly, because there is nothing here, and suddenly the events start inside your detector. Because the muon, up to that a neutrino, and neutrino will not do anything in your detector. And then suddenly you start, this is the detector, okay? Whole thing is a detector, and in the middle something started. So you saw neutrinos are there. Okay. So these are all then atmospheric neutrinos. So neutrino oscillation I told you. So what else we have to do in neutrino physics? Now this neutrino oscillation, see, till that time we thought that neutrinos are massless particles, like photon. They have no mass. But if they have to have oscillation, then they have to have mass. Okay? So the neutrino oscillation that we saw, that solar neutrino problem gets solved, that's because they have to have mass. So that is now called the experiment. So we have to measure the neutrino mass. Now what is the future experiment in neutrino physics will do? They will try to measure the mass of those neutrinos. And also there are three neutrinos, right? Which of the more massive, which is the lightest, which was the heaviest? What is their mass? This is one of the reasons why you want to study further experiment in neutrino physics, more experiment in neutrino physics. Then, what else to be done? There is another puzzle we have seen, right, in the universe from the creation. When the universe was created, matter and antimatter was created in equal number. Okay? I told you at the beginning that when two photons collide, they will produce an electron and a positron, or a neutrino and an antineutrino, or a up quark and an anti-up quark. So they are produced in equal number. But what we see today in our universe is only matter, no antimatter. So what happens to that antimatter? What happens to them? They must have been there in the beginning of the universe. What do they disappear? To explain that, what you call this, that means matter and antimatter doesn't behave equally. But this is called in our language CP violation. But I am not going to talk about that, okay? Because I think this is not enough to. But there is some property by which matter and antimatter behave differently. If that happens, then this antimatter could have disappeared and possible. So we want to study that, and in neutrino also it is possible or not. That means if the neutrinos and antineutrinos, they behave same way or differently. That also we want to understand. So these are very important questions, because if we can show that neutrino and antineutrino, they behave differently, their properties are different, then only we will be able to explain why there is no antimatter today in the universe. Okay? So this is another strong reason, fundamental reason why we have to study neutrinos. So who are the experiment is doing that one? Let me just show. So there are, this is actually the Nature article some few years back. They talked about 4 important experiments that is coming up in different parts of the world to understand neutrinos in a much better way. Where are these 4 experiments coming up? They have listed here. This is one is called JUNO, J-U-N-O. Okay? This is coming up in China. They are making a detector for studying neutrinos that is coming from reactor, putting the detector from the reactor at a distance of 50 kilometers and studying them. So they will be studying neutrinos. They will be able to, this experiment will be able to tell us which of the 3 neutrinos are the heaviest and which one is the lightest. That answer they will explain. Then there is INO, that is all about, this exhibition is also part of that, India-based neutrino observatory. Their plan is to set up an experiment also to understand that which of the 3 neutrinos are the lightest, which one is the heaviest. Okay, this answer. Then there are experiments called DUNE. Okay, deep underground neutrino experiment, DUNE. This is happening in United States. So they will see I told you this JUNO will use reactor neutrinos. INO will be using those atmospheric neutrinos that I talked about. So they will be using atmospheric neutrinos. So we don't have a neutrino source here. We use that atmospheric neutrinos. The DUNE experiment in United States, they will be using neutrinos from a source, from accelerator. So that is near Chicago. They will produce those. There is the accelerator called Fermi National Accelerator Center. There they will be producing those neutrinos. And they will send that neutrino beam through Earth to a distance of something like 1,300 kilometers away. In another part of United States called South Dakota, and there is the underground laboratory. There they will be detecting those neutrinos. So they will be doing, and this experiment will be studying if the neutrinos and antineutrinos, they behave differently. Okay? That's all they will study, whether they are same or they are differently. This question. And then there is another experiment will be coming up in Japan. Japan has done a lot of neutrino research, and this is called HyperKamiokande. Hyper, because they have already an experiment called Kamiokande is running, SuperKamiokande. Now it will be much bigger than that, and they will be doing this experiment in Japan. They will also studying whether these neutrinos or antineutrinos are same or differently behave. So these are the 4 experiments that is coming up in the world in next 15 years. Neutrino experiment takes long time. It will probably start giving result by 2030 and continue up to 2040. And the construction of some of them has started. For example, DUNE experiment construction has started. JUNO experiment has started. INO is not started because there are some politicians in Tamil Nadu who thinks that neutrinos are bad for human beings. So he is actually stopping this project to happen. He has gone to court and got injunction. So we can't really start that experiment. But this is a basic science experiment. If it happens, then all the students, maybe you will see the next speaker will show you all these beautiful detectors, instruments that we are building, that you all could have gone and put your hands there. Some of our young kids could have opportunity to become a scientist or at par with the rest of the world. But our politicians, not all politicians, I would say, some politicians, they think that is because of their own, because they probably need votes, so they go and tell lies to the local people, and they are unfortunately farmers. They don't understand neutrinos or anything, so they believe more to a politician than us, and they think it will do bad, so we have not been able to do anything. So imagine a country in a modern India we are still not able to have that kind of scientific mindset that we should have among people, so that they will be able to differentiate that which is good, which is bad. That's unfortunate, but maybe this kind of lecture, this kind of seminar, this kind of exhibition going from different parts of the country will make people more aware of what science can do, and then all those nonsense. Okay, so this experiment, and these are actually could have put India into the world map, because these are very important experiments. Each of them, as I told you, have will answer a basic fundamental question about neutrino physics. Okay, so this is some of the things. So here for example, I'm saying that Fermilab experiment. They are producing the neutrino beam in that Chicago in an accelerator, and then sending the beam through the Earth, okay, 1,300 kilometers, and then somewhere in South Dakota, in another state, this is in state of Illinois, who knows the map of United States, and this is in the state of South Dakota, west side. So they are going 1,300 kilometers, and while moving through the Earth, they change their properties. As I told you, neutrinos oscillate. Okay, so neutrinos oscillate. So what they will send from here is muon neutrinos, pure muon neutrinos. And in this detector, they will try to look if there is electron neutrinos. That means if the muon neutrinos is getting converted to electron neutrino. And also they will send muon neutrino and muon antineutrino. So that means they will be able to also separate out, study separately muon neutrino and muon antineutrino. So whether the neutrinos and antineutrinos behave similar way or they behave differently, that also they will be able to study. So then they will be able to establish the CP violation and so on. So this experiment is going on. Okay, this is HyperKamiokande, underground. Again, all underground. Okay, HyperKamiokande. Probably if they get the funding, they have not yet got funding. By the way, INO is completely funded by the government of India. So we have all the money. We can start tomorrow if that politicians, stop spreading nonsense. But this is not yet funded by the Japanese government. But if funded, they will start construction from 2026. And this is something like half a megaton, 520 kiloton of water, very ultra pure water. They keep it and they watch the water from all directions inside with many, many eyes. Those are looking for light. When a neutrino comes, they will produce an electron, okay, or a muon, and this electron or muon will produce photon called Cherenkov light. And these detectors all around will detect that, and then we'll study that one. This is the Juno experiment in China. This is actually different, not water, not this. This is actually a liquid scintillator. A liquid scintillator is a detector. When any charged particle inside that, it will produce light, okay, and scintillating light. And so this detector, this is actually 20 kiloton. So you see, neutrino detectors are all big. And you know why it is big? As I told you at the beginning, because neutrinos hardly interact. So even if you collect handful of events, your detector has to be big, and you have to have a strong source of neutrino. This has to be satisfied. Anyway, so this detector, and this is INO, India-based Neutrino Observatory. This is supposed to come under a mountain. So we have to make a tunnel of 2 kilometers, go under the peak, and then why we have to go under the peak? Because you have to stop all the cosmic rays, as I told you beginning. That is the reason you have to go always underground. You saw all the other experiments also all are underground. And you had the covered. Now, once we saw we are going underground, then these politicians started spreading all those rumors. Oh, why they are going to underground? They must be hiding something. That's why they are going underground. So they will be doing something very bad for the country. That's why they are going underground. This is the type of message they are spreading. But we have to go underground because we have to stop the cosmic rays from coming. That is the only reason. Anyway, so in that, we will have this beautiful detector. This is a 50 kiloton magnet. Whole thing is a magnet. This will be the world's biggest magnet we will be building. And in that, you will have many, 30,000 particle detectors called resistive plate chamber. Okay? Here is a picture of that one, and maybe it will show you, but it is like this. If this is a resistive plate chamber. It is 2 glass plates, and inside there is a gas you fill, 2 millimeter gap, upper and down coated is graphite, and then when you apply very high voltage, and whenever any charged particle goes through it, it will give a pulse to a pickup strip, which will be putting in this, will be putting on that top. And then if the particle is going through this, then you will get a strip. This particular strip will get hit. If particle is going through here, then this particular strip will get this thing. And they will be all connected to electronics. And then there will be data acquisition system and so on. So it is a massive electronics, data acquisition system, monitoring system, all will be developed by the engineers from this country. In fact, some of them who are working on that, two of them are sitting here in the top, who have built a major part of this thing. So this gives them excitement, that we are doing something fundamental, something from the very basic, from the beginning, okay? And then we are not repeating all the time. We are doing something new. And of course, when you do something new, the challenges of doing something come, and then you solve it and proceed. So this whole excitement of doing this experiment would have been there. There are other experiments are also coming in neutrino physics. Just to show you, there is one experiment in South Pole. This is called IceCube. The neutrino detector are big. You know how big is this detector underground? This detector is a square kilometer in area and roughly a kilometer in height. So called a kilometer cube. That's why I call IceCube. It is in the ice. This is also same thing. These are all photodetectors that are there inside the ice, and charged particle comes, interact in the ice, produce electron or a muon, they will produce light, and those are collected by this photomultiplier. This is called this will detect very strong, ultra high energy source of neutrinos in the sky. Okay, this is a cosmic ray experiment, ultra high energy neutron in the sky. So they are all doing this. Okay, so this is IceCube experiment. So now let me just tell you two transparencies. I have doing this for many years. Why India should do such an experiment? This is very important. So of course, as I told you, this is a very exciting area. I mean, you will be working with the world scientists at par with them in a fundamental research. So excitement of carrying out front-ranking research in the exciting field of neutrino physics is the key reason why you want to do that. We will address a key question of neutrino physics, that is the neutrino mass ordering. Which of the three neutrinos is lightest? As I said, which one is hardest? This will help pick up the correct theory beyond standard model of particle physics. But this is not the only reason. This is the physics reason. But look at that. We'll develop various cutting-edge technologies while developing this detector. Okay? For example, that massive 50 kiloton magnet I showed you, we have to build ourselves. These 30,000 particle detectors, we have to build from scratch using our Indian industries. The sophisticated state-of-the-art electronics, online monitoring, data acquisition system, all things. You have to know all the detector, whether they are operating all the time or not. What is their heartbeat? What is their condition, health, and so on. So science students across the country will have the opportunity to participate building each of these components from scratch. In fact, many are already doing it. It will create an ambience of doing things in your own hand. Okay? It's a confidence, give us that we don't have to look for science only for abroad. Science can happen in the country also. So a culture that is lacking in India. We do not have much culture of doing experiment. We have theory. Many theorists are there. But if you see to build things in your own hand, to do experiment yourself, that culture is missing. And this experiment will give you in a massive way support for that exactly. This is not the only reason we are doing this experiment. This also, no single institute in India has the ability or resources of doing it alone. So already 25 research institutes, universities, IITs have joined hands to build INO laboratory and the ICAL detector. Some are developing detector, some electronics, some working on various engineering aspects, some optimizing the detector using computer simulation. So different kinds of people you need. Culture of cooperation and collaboration is another benefit that will emerge from such a mega science project like INO. Thank you.